Hello everyone. Welcome to our presentation. I'm Pietro Borrello from Sapienza University of Rome.
And I'm Andreas Kogler from Graz University of Technology.
Today we will present you dynamic process isolation. And during the talk, we will talk a lot about Cloudflare workers.
That's a good keyword. So what actually are Cloudflare workers? Cloudflare workers are an edge computing system, one of the best, and basically they deploy servers in between your origin server and the clients. So the idea of an edge worker is to intercept your HTTP requests and modify them. That can be used to basically run statistics, or in common use case would be to insert ads into the actual body of the request. Since this is a high-performing system, a server, they deploy so-called in-process isolation. What's the difference in between in-process isolation and classical isolation is that we remove the overhead of classical virtualization by putting every worker into the same process.
Wait a minute. Are you saying that you basically ship like every single worker in the same process and every single user runs his code like in the same process?
Exactly.
But wait. Is this vulnerable to Specter? I mean, it's like classic case.
No, we have some preconditions there. We disabled all the local timers, so you don't have a chance to measure time. And furthermore, we also will limit the requests you can send, the sub-requests you can send, and also the memory you have available from each worker. But if you were right, and there would be a Specter attack possible on our system, we would need a low overhead solution in order to keep up with the high performance goals of our system.
I'm not convinced, I would say. Like, do you know how Specter works?
No, but maybe you can tell me more.
Yeah, no, we should start from scratch. I mean, okay, let's start from like caches, like super simple one-on-one stuff. Like you know, caches, like they are like on all CPUs, and they are like basically a fast way to access memory. So every time you access memory, for example, you will try to load something, and if it's not in the cache, we will have a cache miss, then goes to the RAM, and we will have a request to the DRAM that will try to load the data in the cache. Once the data is loaded, then you have a cache hit. So in the second access, for example, it will be like a lot faster, since access is the DRAM. You will have like a slow access time, and like accessing the cache directly, since the cache is loaded, you will have a fast access time.
Okay, I understand what caches are, but this is not an attack. What can I do with it?
I know, like one thing per time.
Oh.
But let's try to like go a bit like step by step with, let's talk about flush and reload. So let's assume that I am an attacker and I have some kind of shared memory with you as a victim.
Okay, what shared memory? Is it like shared libraries you load into the same process, like something like that?
Yeah, any kind of shared memory that is like...
Anything?
Yes, any kind of physical page that is like shared between us.
Okay.
So let's assume like we have some shared memory that we both access, and I want to infer something about your behavior. So as an attacker, I can flush the memory so that it will not more be in the cache.
Okay, yes.
So once the memory is flushed, then, okay, the victim runs, and maybe the victim accesses that like cache line in the memory and loads again that in the cache. And then if I access that, I can like kind of infer based on the like access time if the victim accessed that or not, so that I can infer some behavior of the victim.
Okay, that sounds cool. But I still don't get what this has to do with speculation. It's just a memory access and the classical cache used in a different way.
Okay, I see you. You want Specter.
Yes, show me Specter.
This is Specter.
Okay, so this is Specter. So let me rephrase. Let me look at that. So we see here a branch with an, I assume, out-of-bounds access, and we have some index which goes into a data array, which we then transform in some sort of lookup table.
Yeah, we have clearly like just two assumptions in this like code snippet. We, as an attacker, can control the index where the data is like accessed. Obviously, the data is like accessed with some checks. So like, there is a check that checks, okay, is the index inbound or out of bound? And then the second assumption is that, okay, then the victim code will like use the index in some way. And here we are like simplifying a lot with like showing that the victim just accesses like any kind of shared memory, like indexing with the data value. So here, LUT stands for like lookup table, and it's just a way to like model this behavior.
And the lookup table is the shared thing you mentioned in the beginning.
Exactly that.
Okay.
So I know you want some more details on that. So let's look at like how it works. So we have like our lookup table, that's the shared memory, and like for example, we have some victim data. Like the green one is the like data that the victim should use, and the red one is the data that we are not supposed to access as a victim, since it should be secret data.
Exactly, but I can see there's the index width smaller than 4. So basically, you can't access the key, the secret data there.
Yes, so we have a check that like should prevent like the secret data from being accessed. But in like modern CPU, there is this thing called speculation. And basically, a CPU tries to predict where like a branch will go to like optimize stuff and like being faster while executing. So what happens when you execute? So okay, the first time like the CPU will know nothing, so the speculation like doesn't matter here. But then like after it gets where is the right direction of the branch, the CPU will like start understanding that okay, this branch is likely taken. So we will execute our code and we will dereference like both the data and also the like lookup access, and we will load the cache line there. So what happens after? We will continue like our code, and the CPU will continue speculating and executing the right side of the branch, and then afterwards, the CPU will like be really like sure that
right?
really confident that the branch is going to be taken. So what happens? Like when the index is 4.
It should have borrowed. It's like the index check is still there, so we should not access any secret data.
But the CPU will think that data is accessed. So we'll access K, and then, okay, we'll continue accessing with the root access, and then load the K cache line here.
But wait. That's not how CPUs work. You will never see the access because it's reverted, because speculation can be reverted in CPUs.
Yeah, so speculation is reverted, but not the effect in the cache line. So the cache line will stay there, and the attacker can observe that.
And then I can use the technique you showed in the beginning to infer if the line is in the cache.
Exactly.
Okay. So this is now the whole Specter, like Specter V1. But actually, I looked a bit into it, and there are some mitigations against these Specter attacks. There are different levels. So we have application level defenses, which are basically newly added instructions you can add to your code in order to stop speculating. If you add them near your branch, you will stop the speculation of the branch. Furthermore, there are also like system level mitigations where you have like operating system trying to clear the prediction state after a process switch, like a context switch. And finally, in a perfect world, we would have hardware mitigations where we don't need to care about Specter at all.
Okay, so I see that, but like all of these mitigation have nothing to do with something that is in the same process. You're basically saying, okay, if you're isolated, we can mitigate it, but we run in the same process. So like, what's the point of all this?
I see your point, but we thought about it. First of all, we freeze the execution time during the worker execution, so you don't have a timing primitive. Furthermore, you have no native code. You can't flush and reload, basically, because you're just bound to JavaScript. And then we also don't allow for shared memories, so we don't have these lookup tables anywhere in the Cloudflare environment. And finally, we do not allow for multi-threading, so you can't build like a counting thread that artificially makes a timer.
So you're basically saying that I cannot like measure timing while I'm executing?
Yes, you can't measure it, so you can't leak.
No, I don't think that's true. That's not true. Like, follow me. Okay. So we are saying, okay, we are in the same process. I'm an attacker, and like you're a victim, and I want like to like leak the memory from you. So just assume that I can like transiently like victim data.
I still don't see how that helps me.
Okay, I cannot measure time, but what if I like ask for time? So let's assume I have like a third party where either I can ask for time, but okay, you could say like you can block that or like whatever. But what if I just send requests to the party and that party keeps the time from me and then tells me like, okay, this is like fast, this is slow.
So just suggesting that we have like a third-party server measuring the time, and that third-party server should distinguish a single cache hit from a single cache miss. That will never work.
Okay, I see your point.
Yeah.
But I'm not saying this. I don't want to distinguish a cache miss, a cache hit. That would be like super noisy, super hard.
That's the idea, right?
No, we have this thing called amplification. So we can like literally amplify the signals that we want to measure, so that we measure something that is much more like lasting in time. So, for example, like I can give like an example. We can, okay, you say I can measure a cache hit, but if I just measure, I don't know, 100 cache hit or cache misses, they are much different.
But wait, cache lines are limited, so you cannot scale it arbitrarily.
Yeah, that's why we have a second way to do that.
Oh, okay.
Let's assume that I want to measure something. What if I just repeat that something like n times? So let's have simple look of the code. That's simplified, obviously, but
Yeah.
let's assume, okay, we have like two cache lines, a cache line A and a cache line B. So I want to leak like this secret bit. And okay, let's assume that both of those cache lines are not loaded into memory. So what if okay, transiently like execute Specter, and I have some transient execution where transiently I can like either access A or B with the if statement. So let's assume that secret bit, for example, is 1. We will have this if statement that will execute transiently, and we will access the cache line A. So we will have a cache miss, and then like, for example, transient execution like dies. So after that, we will have like an access A that is architectural. But since we already loaded the cache line A in memory, that access will be fast. So we will have like a slow access and then a fast access.
Like in the beginning with the cache.
Yes.
Yeah.
But in the second case, let's assume that instead secret bit is 0. So we will take the else branch, we will like read from memory B. So we will have slow access. And then after that, we will have another slow access due to the architectural read of the line A. So in every loop iteration, we will have like either 1 or 2 slow accesses.
Okay, I get that. But how can you, what do you get out of it?
Yeah, so you can like execute that multiple times. So if in one iteration we have either 1 or 2 accesses, then in n iteration you will have either n or 2n slow accesses. And if you scale n to like a big number, you can like increase that like almost arbitrarily, like up to milliseconds timing differences, so that you can observe like the slow accesses.
Okay, I give you that point that you now have like a primitive where you can amplify the latency. But still, we're running in JavaScript. JavaScript has no native code execution. So how do you either flush and reload the memory? Because you don't have flush instructions or anything like that. We also don't allow timing primitives, so you can't even build eviction sets with that. So what do you do there?
I see your point, but you don't need to like have such precise timing primitive, like just to evict memory. Like for example, we just can like iterate over huge arrays to like evict the whole caches, like with like just iterating with huge arrays. So
yeah, okay, but still, if you look at Java is a highly optimized and de-optimized language. So it has assumption on variables it uses to optimize it. But if these assumptions are broken, then it's de-optimized again. So how could you cope with that?
Okay, you're saying, okay, the JavaScript engine, V8 in this case, that's the engine that Cloudflare uses, like observe the code, like breaking invariants. But we can just like execute our attack behind a mispredicted branch so that the JavaScript engine actually will not observe our code breaking those invariants.
Okay, yeah.
Furthermore, we can just avoid like nasty optimization, like inlining that will ruin like our branch predictor states by using like huge functions that are just not inlined, or like having like big functions that are not fully optimized by the JavaScript engine.
Okay, so I see that you have some countermeasures against this complex thing of optimization and de-optimization. But still, JavaScript objects are indexed by 32 bits. How can you ever access a 64-bit address in order to attack your worker in the same process?
I see. Okay, so JavaScript has this thing called like pointer compression in V8, where they basically try to save memory, like representing pointer with 32 bits. So almost every object has this, but the keyword is almost.
Oh.
Not all the objects have like just 32-bit pointers. There are some objects, for example, array buffers, that have by design have to be able to store 64-bit information so that we can just like leverage those objects to like index the memory with 64-bit pointers so that we can use them. And moreover, we can confuse like branch predictor on the types of those objects to create a speculative type confusion and like leak from memory.
So that sounds highly complex. Can you give us more details on the type confusion?
Yeah, I see that. But let's have a look on like how JavaScript internal implementation works.
Okay, what do I see here?
So yeah, here you see like a simple object. Like for example, let's assume that we have an object with an integer and a pointer to like an array buffer. So how is that like laid up in memory? We will have the JavaScript object and like with the integer and the pointer.
This pointer, is this the 64-bit pointer?
No, this is still a pointer to a JavaScript object that is 32 bits. And this pointer will point to the array buffer object that contains itself the 64-bit pointer.
So that's the pointer we want to
that
target.
Second one is the pointer we target. So this second pointer is the pointer that is the reference to. when you go to access the 64-bit memory. So we have like actually two memory dereferences when you do like obj.pointer of 0. So now, let's assume that we have a second object. This second object will be really, really similar with the first object type. We will have like integer, and all the other fields will be the same fields. But this second object will have an integer instead of the like array buffer pointer. And with this integer, we can literally control this 32-bit value. And with this integer, what if we just make it point to any chunk of memory that we control to create a fake array buffer, so that in the fake array buffer, we will have the target address that we want to dereference. And with these two steps dereference, we can access any target memory that we want.
Okay, I think I got the idea, but still, these are two different types of object. JavaScript keeps track of which type of object it is in some sort of meta information. So
yes.
How would you confuse them? Like type what? Type confuse?
How JavaScript can check that with a branch. We have a branch here.
So basically, this branch is similar to the branch we saw in the beginning by the Specter tag.
Yeah, we just don't mispredict on the bound check, but we mispredict on the type checking. So it's just different misprediction, but just a branch.
Okay, whoa. That sounds, again, highly complex. I don't think that can work. Have you tried that out? Can you show me something like that?
We have a cool demo. So here we're like, at the beginning of the attack, our attacker has to build the fake object primitive. And then after having to build the fake object primitive, it can then leak memory on the 64-bit address space. And here, for example, we leak some strings from the binary.
So wait. So you're within JavaScript, you have an attack primitive that can leak strings from within my binary?
Yes, from any binaries running D8 or like Chrome or anyone.
Okay, that sounds dangerous.
Yes. So basically, with this attack, we are able to leak like remotely over the network 120 bits per hour. So that means that in the like average and default like Cloudflare worker runtimes of 30 seconds, we leak at least like 1 bit of like victim data, just by using this particular type confusion to leak from like the whole memory.
Okay, that sounds really bad. So I have to think about how to mitigate that. Maybe stick with me. So again, You told me in the beginning that you have this attack worker and this victim process. And what if I place some sort of detector in here that basically observes each worker of the system? And if now somebody like you tries to make a transient access to a victim process, I simply detect it and then isolate the attacker into its own process, basically its own virtual address space, and then I can use the Specter mitigations from the beginning.
Okay, that seems cool, and it seems like if you say like that, it should work, but I have so many questions in my mind, like, this is super complex. For example, how do you even observe like the stuff that every single runner is doing? Like,
that's actually a really good question. Fortunately, modern CPUs have something built in like that's called performance monitoring counters. These are counters, they are 64-bit wide, which count microarchitectural events. So you can think of a microarchitectural event like branch misses.
So is the branch misses like the branch I speculate on to leak the data?
Exactly. So basically this misspeculation where you have then this transient window. And for instance, if we take a comparison between a production system and an attack, we can see that the branch misses are actually highly different between the production system and the attack. So you can clearly see on the left in the histogram that we can simply separate them by a threshold. Furthermore, we also could use like branch accesses, and similar to branch misses, a normal program running would have much more branch accesses than an attacker because it's really small in its size.
Wait, but like, what if I have like huge code base that is running? Like, how does it work?
That's again a good point. We need to normalize them per code executed. Otherwise, a bigger program would, for instance, have more branch accesses and more branch misses. So we need to normalize them.
Okay, that seems okay. But okay, I know these like performance monitoring counters, they are super slow. What's the overhead of like such a solution? Like,
yes, that's actually true. There are different interfaces you can use to query these performance counters, and all of them have different performance implications. In the end, we used the last one, the RDPMC instruction. That's an instruction you can actually use in the user space if the kernel is configured correctly. And overall, we evaluated it on the Cloudflare system with real production loads, and it showed only a 2% performance hit. It's still a hit, but it's acceptable for the environment.
Yeah, that seems reasonable, I would say. But okay, but does it work? Do you literally like detect the attacks? Like,
That's a bit more complex, I would say, because you have a trade-off between the detection and the leakage rate.
Okay.
So on the left, we see an image where we see on the top an attacker. And the leftist, the most left sample in this trace is basically the attack you showed in the beginning with the 120-bit leakage per hour. And you can see in the bottom what the detection does. So if we use a simple threshold, the attack is immediately detected since the value for the counter is way beyond the threshold.
Yeah, that seems really high, but what if I just, I don't know, slow down my leakage rate, so just do a lower amount of branches?
So you mean you reduce your throughput from the attacker's point of view to get below the threshold?
And yeah, and then I trick the detection. Like,
yes, that's actually what's the graph showing, is that how you can reduce your leakage rate from the 120 bit per hour to try to get below that threshold. However, the threshold, the detection actually works so good that if you reduce the leakage rate to get below the detection rate, the attack is infeasible because you only have a 30-second execution window where you no longer can exploit this leakage. So overall, I have to say that this defense gives a strong reduction of leakage rate and makes these attacks basically infeasible.
Okay, that makes sense, but we are still talking about like a defense. So like, do you just randomly isolate something if there is a false positive? Like, how many false positives do you have like while running?
Yes, this was also a concern. So basically, we try to evaluate this attack and defense, more the defense, on the CPUs used in the production systems. And we can see that based on the different counter values, we get more or less false positives, like we expect. Some programs have more cache accesses, some have more branch misses or something like that. However, for a threshold of about 40K, we get a low false positive rate, about around 1%. So this is again acceptable since we don't pay for false positives. It's just in performance impact. We wrongly isolated them.
Okay.
The program still works fine.
That's cool. Okay, that works. But okay, we're basically saying that like you, I don't know, normalize about the code I execute. That.
Yes.
But what if I try like to trick this threshold that you have? Like, for example, what if I just span my attack over like multiple code pages so that I just like increase the like denominator of your formula with the high TLB accesses and then just reduce your threshold, like, and then it will be below.
So let me recap that. So you're trying to say that if we basically get the number of code executed up to do the normalization, then our factor will got below the threshold.
Yes.
That's a really good idea. We evaluated that in native code, as you see on the left. There we added native code pages in between the attack. And we can see that we see a reduction of the actual threshold factor after we added around 90 pages. Keep in mind that these are native code pages. And that's the reason why it's not working in JavaScript, because JavaScript won't compile these large code samples into optimized code. It's just interpreting it. So in order for your attack to work, it must be compiled in order to get this misspeculation out of it.
Yeah, so you basically break the attack. Makes sense.
So yes, I'm solid now, so let's build it.
I accept that.
So overall, how is this implemented in the Cloudflare ecosystem? We can see on this build, on this picture, a short systematic overview of the system. We can see on the left side, we have this inbound HTTP proxy, which basically accepts HTTP requests. We have then some scheduling and routing, and these V8 isolates, how they are called, are basically the workers running in one process. After the HTTP packet is processed, we pass it forward to the outgoing proxy and pass it to whichever destination the packet should go. If we now detect a malicious worker, we can simply isolate that into its own process sandbox, which is isolate and communicate with an IPC connection, inter-process communication, and deploy these process isolations as they help against Specter. Yes, so overall, this brings us already to our conclusion. So we have shown you that remote Specter attacks were possible on Cloudflare, in the Cloudflare edge worker systems. However, we developed a mitigation that does not only work against V8, against Specter V1, as we've shown you, but against all these Specter variants. Finally, this was also a collaboration with Cloudflare. So this is actually deployed in a production system, and it resulted in a scientific paper, and the QR code is actually linking to the paper. So
it works.
Yeah, it works. Yeah.
So thank you, everyone. And if you have any questions, we will be happy to take them.